Welcome to part 2 of my video about Archimedes. If you haven't watched part 1 yet, I suggest you do so right away because they are actually linked together. Right, I'm looking for a beach now in Syracuse. There aren't many, but I found one. You see, right behind me, there's a beach. So I just want to explain something rather important to you. So, one of the stories goes that Archimedes was actually working on a mathematical problem. He was drawing circles in the sand, a bit like these ones here. I've just drawn them a bit more poorly than Archimedes, and he was so engrossed in solving a mathematical problem that he was like fixated. And then a Roman soldier came along. This was the Roman invasion of Syracuse, 2012 BC. A Roman soldier came along and ordered him to move with a sword, of course. Archimedes wasn't having it. He was like, no, I'm so engrossed in my problem. The Roman soldier was probably about to trample all over the circles when Archimedes said, "Don't disturb my circles." Well, the Roman soldier wasn't really impressed and killed him. That's how Archimedes died, unfortunately, by a Roman soldier, 2012 BC. That's why Archimedes lived all his life in Greece, and after that, Syracuse became part of the Roman Empire. So I'm going to leave the scene of my circles now. So Archimedes' story was so powerful that it inspired other people to learn about mathematics. Sophie Germain being a notable example. She read about Archimedes and was so fascinated as to why Archimedes refused to move, essentially died for the sake of trying to solve a mathematical problem. And mathematicians like Sophie Germain thought, well, if this mathematics thing is so important, so fascinating, that it's worth giving your life up for, why don't I investigate what this is like? So, yeah, I had to ask myself, would I have done the same as Archimedes? So if I was engrossed in a mathematical problem and someone basically ordered me to move, I'd probably move. I'm not sure that I'd want to sacrifice my life for mathematics, but there you go, that's just me, isn't it? Should we just see what's on the end of this pier here? Yes, why not? There you go, there's the beach in question, and if I just show you some more of the scenery, isn't that lovely? Wasn't lovely at the time for Archimedes, of course, but it's lovely to be able to tell the story. So this is an Archimedean spiral. You can't quite see it yet. If I spiral around, yes, there we go. I'm just going to pan out, and you'll be able to see the Archimedean spiral. While I'm out of breath, you hear me panting a little bit because of the video that I'm just about to play you. That's right, I found a huge Archimedean spiral and decided to run around it. No particular reason, it's just there. People climb mountains because they're there. I run around Archimedean spirals because they are there. So one thing I like about being on a beach holiday or an island holiday is boats. Yes, who doesn't love being on a good boat? Okay, there's a big one, isn't it? There's a cruise ship, and then here we are. That's more my thing, a luxury yacht. But what keeps these things afloat? Well, it's Archimedes' principle of flotation, and I'm going to explain that to you right about now. So for the next bit, I need to demonstrate one of Archimedes' principles. For this, I need a pool. Yeah, this one will do. I'm not going to use a bath because, well, I just have to have a pool. So I'm going to use the pool to show you what Archimedes' principle is all about. So here I've got a bottle, it's an empty bottle. So I'm just going to demonstrate what's going to happen if I just set this into the pool. We reckon it's going to float, don't we? Here we go. Yes, there we are, floating. Nothing special in that, is there? Well, let's just fill it up with some water. There you go, it's not quite half full, just under half full, but it's filled up with some water, isn't it? Now I'm just going to put it onto the pool and see what happens. Let's reverse the camera, shall we? There we go. There. I don't really want to put my camera down too much lower, but can you see it's floating still? Not quite sinking, but it is still floating. Right, now I've filled it right up to the top, so it's actually a completely full bottle of water. Let's see what happens when I put the bottle of water inside the pool now, shall we? Again, let's reverse the camera. There we go, here's our pool, here's our water. Let's just put it in and sunk. There we go. Let's just retrieve our bottle. So this was the most interesting one. I just filled it up a little bit more than half full. Okay, this is the most interesting one because it didn't sink, it didn't completely float on the surface either. This is kind of like what a ship looks like, a boat, cruise ship, whichever you want to call it, because it's long, kind of like this, different shape of course because it's a ship, but you do have a lot of it underneath the water you don't see. That is to carry all the weight, the masses of its cargo and the ship as well, of course. And what happens is, it doesn't sink, does it? It floats. I'm just going to show you again. Okay, so here's my bottle of water, so I'm just going to place it in there, just like that. And what's happening is, yeah, that's just floating a bit, isn't it? Kind of like you expect a ship to float. What's happening is, the amount of water that it's displacing is keeping it afloat. Yes, you heard me correctly. So, in terms of the flotation, you've got to be able to displace the same amount of water that's actually in the bottle itself. That's why if you see the water level in the bottle should be perfectly in line with the water level of the actual pool as well. That's quite amazing, isn't it? And if a ship is constructed like that, it will sail safely to sea. If there's too much water in there, like the poor old Titanic, it will sink. So a bottle this full, it's got to displace the same amount of water in order for it to be able to float. Whereas a bottle like this, it's actually full of water and it's going to displace the same amount of water when it's in the pool. That's why it won't float, because it's got to displace exactly the same amount of water that's actually in the bottle itself. So it's not going to float, it's actually going to go beneath the surface. A bottle like this, when it's completely empty, well, if it's displacing the same amount of water that's in the bottle, there's no water in the bottle. It doesn't need to displace anything. That's why it just floats neatly right above the surface. I guess one of the morals is, if you need to get rid of a bottle and you don't want people to be able to find it, fill it with water or a heavy substance so that it will actually sink and not just bob up and down on top of the water itself. Of course, I'm just using this simple water bottle because it's a very good example to use. It's very, very light, so it actually doesn't make too much difference to the water it's displacing. If you've got a very, very heavy bottle, which effectively is what a ship is, because of all that, I'm not sure what the construction material is, but I'm guessing a lot of steel, a lot of heavy stuff. Because it's heavy, it's naturally going to go under the water a little bit, isn't it? Okay, but it's just an example. But just imagine this as your cruise ship, and the water inside is all the masses combined of the stuff that's inside it, including all you wonderful people. Now, all this is very interesting, of course, but this is with a simple bottle of water. Now let's do something really fun. Right, so here we go. So, what happened there then? What was all that about? Well, hopefully you saw that there's a lot of water that was displaced by my jumping in. I did curl myself into a ball just to make it a bit more dramatic. So, here it is again. And let's watch that from another angle, shall we? And then let's do the obligatory slow-mo shot. So there's all that water that's been dispersed, and that's basically what Archimedes discovered. Okay, now he apparently gently went into his bath. I didn't. I did a full-on bomb shell into the bath, and it dispersed all of that water. Okay, that's essentially what happens when you launch a ship for the first time. It just goes cascading straight into the sea and disperses an awful lot of water. Ship's of course a little bit heavier than me. So if you look up Archimedes' principle of flotation, it will say something along the lines of, an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. So, as I was submerged, and that's putting it lightly, I did feel an upward buoyant force. What you'll also notice is that I didn't completely sink and stay at the bottom of the pool. Don't forget, humans are made up of a lot of water. I don't know the exact percentage. But that counts for the fact that actually humans are quite buoyant when they go into a pool. That's why we find it generally quite easy to swim, because we don't sink all the way to the bottom. Things I do for maths. Well, hope you enjoyed that little experiment. Wet my shirt now. Got to wait a long time for it to dry out. So, end of the line. I hope you enjoyed my video about Archimedes in Syracuse. I enjoyed making it, of course, but I just find the whole idea fascinating, that it was Greece and suddenly the Romans came along and this played its way somehow into the magical story that is Archimedes. Thanks very much for watching, and I'll see you again. Bye bye.